survey from Indiana University. And he's going to tell us all about how Atherton Island was formed and stuff like that, right?
I hope to do that. I hope to do that,
Atherton
yes.
is so cool. So, if you've not been to Atherton Island, when is it scheduled to be open to the public? Do we have a date yet?
No date yet.
No date yet?
No,
Okay,
hopefully in June.
Oh, that's soon. Eventually it'll be open so we can all just go and hang out there and enjoy nature, because it is a lovely place. So.
And if you want to see some of the things, this is a photo from probably a couple of years ago, down in one of the creeks at the natural area. So, again, Phil knows me pretty well. So if there's ever any, I love going in the field. So it's better than up here me blabbering on for 45 minutes. So, well, thank you for being here. I really appreciate the opportunity. So, as mentioned, I'm Henry. I'm from Bloomington. So I'm with the Indiana Geological and Water Survey. We're sort of originally we were with the DNR going all the way back 175 years. Switched to being with the University in Bloomington, although the survey has been in Bloomington for like 175 years. So, and I do geologic research, of course, in the state of Indiana related to the glacial sediments. So I'm going to talk a lot about those today because that's the big story. The big part of the story of Atherton Island is the history of ice sheets, of glaciers advancing and retreating. So I wanted to just start by showing a really nice artistic image. A lot of you, well, I guess just a show of hands, how many have had some geologic background? Okay, so you guys know the geologic time scale, right? And I like to show this because it shows really two main intervals of time in Indiana where where we either preserve a record of geologic history. And the most recent of those, if you haven't seen this type of scale before, so the oldest rocks are at the bottom here. The Earth is a little over 4.5 billion years old. And as you go up through the rock layers, the stratigraphic column, we would say, you get younger and younger. So at the very top where the truck is, that's today. And so just that last little bit of geologic time, which we call the Quaternary period, it's about the last 2.5 million years of time. And that's defined as the coming and going of large ice sheets, mostly in the northern hemisphere. The remnants of those being like in Greenland and some of the mountain glaciers around the world. But we're in an interglacial climate, so I'll talk a little bit about that more in a minute. But in Indiana, we have a record of that last couple million years of Earth's history. And then you have to go all the way back into the Paleozoic era during the Silurian through the Pennsylvanian periods to see the bedrock that underlies us. So we have just a snapshot here in the state of sort of two main different periods of geologic time that are recorded. So again, as I mentioned, my expertise is in the Quaternary, so the most recent period. So I won't really actually talk a whole lot about the bedrock story. If you have questions about that, I can try to answer, but most of the slides today are going to be related to the glacial history. And so I want to go through a few things, just sort of historical things. Hopefully it's not too basic for everybody, but we have to think about the last couple hundred years of time and how advanced we are today. But relatively recently, this is the mid 1800s. This fellow here, he was one of the big proponents, Louis Agassiz, of the whole concept of that we had glaciers that were much bigger in the past than they are today. So he was in Switzerland in the Alps, and he noticed that you could see the modern glacier up in the valley, but he made some just simple observations about the landscape and the type of material that was on the surface. And he noted things that we call erratics or drift boulders, as he called them, things like this big piece of rock that was that we know now was transported from up further high in the mountains down into the valley. So he said, this rock, why is this here? And it was carried by ice. So he had that observation. He also saw things like striations, which are like scratches on the rock, essentially, that indicate that material was once at the bottom of a glacier. And also landforms, so things that are composed, features on the landscape that are composed of glacial materials. So you may have heard of the term moraine or terminal moraine. That's just a ridge of sediment deposited by a glacier. And so he noted these things and said, there's got to be something here in the geologic past that moved this material and caused these landforms to form. And we had sort of this same thing in the Midwest a little bit later in the 19th century. So T.C. Chamberlain and Frank Leverett were two of the early pioneers of glacial geology in the Midwest. This is in the 1880s, 1890s, and they sort of learned from Agassiz a little bit, and they saw the same things. They saw big boulders in the fields, and they said of rocks that aren't native to Indiana, right? So rocks essentially from Canada that were not native, and they must have come a long way. So they had these observations again a long, long time ago, late 19th century. And I know it's a little hard to see, but this wonderful map from 1898, and again, I can share these slides with everyone if you want to zoom in, but this is a map of the whole North America, all of North America, showing Leverett in 1898 how big the glacier was at its maximum limit. So even again, 125 years ago, 125 years ago, he recognized the spatial scale of this glacier, this ice sheet. Ice sheet is basically just a really big glacier. Okay, so I know the text is a little small there, but they made observations that were related to what Agassiz had brought up, but they also noticed a few other things that suggested there was more than one glaciation. So they observed different areas of the landscape had different amounts of erosion, essentially, by stream networks. And so, and different levels of preservation of different types of glacial landforms. And they also saw intervals in stream cuts, mostly, of old soils that were between different sets of glacial deposits, okay, that indicated there was some period of time between these successive glacial events. So I just want to show you a couple examples of those here. This is actually from Iowa, but you can see a similar type of thing in Indiana. And this is, you can just see, we could spend a lot of time looking at this, but you can just see like the lower left half of the diagram. This is what we call a digital elevation model. It's just a representation of the topography, and you can see how rough it is, and there's a lot of stream networks that are flowing down to the lower left. And then if you look to the upper right, it's a much more smooth type landscape, flat landscape. And so these landscapes are actually of different ages. They've been at the surface for different periods of time. So the area on the right-hand side of the image had a glacier advance about 20,000 years ago over it. And then the landscape on the left had an ice sheet advance over it maybe 500,000 years ago. So there's relative time difference between the two. And you can't see the scale very well, but this is like 100 miles across, this whole image here. Okay. So that's one example. Another example is, I mentioned, there are actually former soils. So these are former indications of the land surface that have sediment above and below them that were deposited directly by glaciers. So you can imagine, like, just today's landscape, if an ice sheet suddenly came and advanced over and deposited sediment over the soil we have today, this is what we have. This is a similar type of example. So This soil here is actually about 130,000 years old. So during the last interglacial periods, or between two different glacial periods, and I'll talk a little bit more about that. So we have going back to the late 1800s, differing lines of evidence. And in the last 40 or 50 years, scientists, not me, of course, but I guess you may not know that, but I don't work on ice cores or ocean cores in Indiana here. But there's other types of information that we can glean from these archives to give us a handle on glaciations of the past, that there have been more than one glaciation, and the timing and the extent of how big the glaciers were. So I really like to show I like to show this image because it's a different way to look at the world. So this is a map looking down on the North Pole. So it's a polar projection. And what you can see here is, so that the circumference, essentially, that's the equator. And if you stare at this long enough, you'll see modern geographic features. I'll try to point these out here. I'll try to reach a little bit. But you can see this is the UK right here. That's England. That's Greenland. And I'm going to move over here for a second, show you. Indiana is basically this little red square there. Let's see, Iceland is here. Scandinavia is here. The Atlantic Ocean is here, and the Pacific Ocean's up at the top. So it's you have to get your mind used to looking at a map like this. But the reason that I wanted to show this is the white areas are former extent of ice about 25,000 years ago in the northern hemisphere. And you can see maybe 20% of the land surface was covered by ice. And also as a result of that, sea level was about 110, 120 meters, so like 300 plus feet lower than it is today, because all of that water was locked up in ice on land. And that's where the color is. So the blues and the greens are where the ocean, where the shorelines would have been, again, during sort of what we would call the last glacial maximum. So again, about 20 to 25,000 years ago. So this is, again, a sort of artist's rendition of what it would have looked like. But again, this map is based on observations of, hey, where do we find glacial erratics? Where do we find moraines? Where do we find different types of glacial sediment? So if we take this image and stretch that back in time, we can see a few things. So I mentioned ice cores and ocean sediments a minute ago. And this is a diagram you probably haven't seen before, and I'll try to walk you through it. It's a record of climate from the ocean that stretches from, in this case, it's 1,800,000 years ago, so that's 1.8 million years ago. On the right, all the way to the left, and that's the modern day, okay? And so there's this curve here with all these numbers. This curve is sort of a sawtooth pattern of, essentially this is ocean temperature, and over the last, again, almost 2 million years of time. And these big fluctuations are changes in the Earth system as we go from glaciated, like we saw in the last image, to like the modern day, where we have glaciers, but they're restricted to like Greenland and high altitude mountainous areas. So you see these big swings in ocean temperature. So the even numbers and if you go towards the bottom of this graph here, that's glacial periods, and then the corresponding odd numbers, and then towards the top of the diagram, those are interglacial periods. So currently we're in an interglacial period. We're at this very warm period between cold periods. And if we extend out in the geologic record. The most recent glacial maximum, we call that the Wisconsin glacial maximum, and it turns out that it was T.C. Chamberlain from before that named these glacial events after states that he thought best represented the deposits of that age. So there's Wisconsin glaciation, and that's the most recent one that, again, was about its maximum was about 20 or 25,000 years ago. The one prior to that, we call the Illinois glaciation. Sorry, I didn't, must not have shown it. There it is. The Illinois glaciation, which was about 160,000 years ago at its maximum. And you can see in between those two, that's the time period between glaciations of about 100,000 years or so. And then in the Midwest at least, we don't have a naming convention for those glaciations prior to the Illinoisan. And unfortunately, Indiana, we didn't make the cut of having a glaciation named after us, but that's all right. So part of the recognition here is to try to get you to think in a long time scales. And also the point that there have been multiple glaciations, and when you actually look at this record and you count all the way back, there's been about 30 glaciations. Now, that doesn't mean that ice reached all the way to Indiana during those 30 glaciations, but there was definitely changes in the Earth system where ocean temperatures and atmospheric temperatures, became warmer and cooler. Okay, so with that said, we can look at just a simple map, and again, this is very similar to Leverett's map from 1898. We can see that the different shades of blue are the different extents of the Wisconsin glaciation, the Illinois glaciation, and then glaciations prior to the Illinois glaciation. So we've already talked about the lines of evidence for why we have multiple glaciations. But in Indiana, we know we've had at least 3 that have impacted Indiana. And the story of Atherton Island contains 2 of the 3, which is pretty cool. So the most recent ice sheet we call the Laurentide ice sheet. And it was, it sort of had its start around Hudson Bay about 75,000 years ago, and sequentially grew sort of outward and southward, mainly because it started sort of, again, in the north and sort of moved south. So it was present from about 75,000 to about 6,000. So you can think of it as sort of starting off as, a very small thing and then advancing south in one big sort of pulse and reaching its maximum about 24,000 and then retreating after 24,000. And the last little bit of the ice sheet was still around just a few thousand years ago, like 6,000 years ago. But again, ice only was in Indiana around 20, maybe between 28 and about 16,000 years ago. So again, this is like a representation of what if you had a satellite view above North America, this is sort of what it would have looked like across North America. And we can produce things like geologic maps that show the different types of sediments. So this is just an image, just a nice image to show you the different types. We don't need to go into the details of what this is, but it's sort of another zoomed in view of Indiana. Indiana is sort of in the center here. It's a little bit hard to see, but Indiana's in the center, Ohio's over here, Illinois is on the left. Lake Michigan and Lake Erie are on the very top of the diagram. And the different colors represent different types of sediments, and I'll describe those in a minute, which are relevant to Atherton Island. So again, the evidence is partly based on the types of sediments we find, which are very unique to glaciers, and also the landforms, which are distinct features on the landscape that we can relate to a specific geologic process. So, and I'll go through a few of these now. So one of the most common types of sediment deposited by glaciers is what we call till, T-I-L-L, and that's material deposited directly, usually at the base of a glacier. And that may be hard to understand, and it is hard to understand because it's hard to observe what's going on beneath a glacier. But you can go to areas around the periphery, and I'll show a photo of that in a minute. One of the interesting things about till is that it's unsorted by size. And what do I mean by that? I mean that it has, and you can see in this image, the scale bar there is like 10 centimeters. So you have stuff that's cobble sized all the way down to clay. So you have everything from really, really small to pretty big. And probably most of you have seen even bigger things, you know, boulders the size of cars, things like that. So you can, that huge range of size of material. And that's very distinctive for, excuse me, material deposited by ice. And this is an example of a photograph at the very, very base of a glacier, at the edge of a glacier in Iceland. And you can see there's, again, similar 10 centimeter scale, and there's big cobbles. These are almost boulder sized material that's falling out of the base of the glacier. So this is where till is usually, till is associated with the very, very most bottom part of the glacier. Typically, although not always, till can accumulate in ridges, which we call moraines, and moraines are formed basically where the glacier stops for a while, stops either advancing or retreating. The ice is still moving, but there's a stationary position where the sediment can basically build up. And so this image here is like a oblique I'm in an airplane looking down. This is also in Iceland. And off to the top of the screen there, that's the glacier, and you can see there's icebergs and a lake. And then beyond that, these little arrows are showing this continuous little feature that you see across the screen here, and that's a former position. Hopefully you can see that because the glacier is just to the north, in this case, the north of it. So that's a former extent of the glacier. Moraines mark former extent of the glacier. Another example from Alaska, modern day example. The size of these things are, they can be really subtle and small. Like a lot of them around here, maybe 10, 20 feet tall. This one here is probably taller than that, and this is just a modern glacier in Alaska. So this. Do you
know which one it is?
Which one?
Do you know which one it is? Which glacier?
This one?
Yeah, in Alaska.
I don't. I could probably find out. I'd have to go back through my notes, but probably I picked this one out because it was the most obvious ridge here out in front. But I can look it up. I can look it up if you're curious. So those are moraines. Another key type of sediment is something we call outwash, which is sediment deposited by meltwater streams. So you can imagine it's a large block of ice. It's melting, and there's a lot of water that comes off. And this is the material deposited by those streams that are coming off the glacier. The thing that's different about this material versus till is that this material is sorted, meaning that it's segregated by size. So the action of the flowing water segregates particles by size. So the big stuff gets sort of left behind in a way, can't travel as far. And then the fine stuff, like the really fine stuff like the clay and the silt, that stuff actually gets carried up in the water column and can go a long way, like can go all the way to the Gulf of Mexico, for example, stay in suspension. So this material is common in Indiana at least, along a lot of the major river corridors. So the Wabash Valley would have been much, much, much larger. Basically the width of the valley, you all know the width of the valley, that would have been full of glacial meltwater depositing outwash during the last glacial period. And if you were to dig it, this isn't from the Wabash Valley, but if you were to have a sand and gravel pit or an exposure looking into those types of sediments, you would see something like this. Much, much different than the river today. Much different type of sediment. Okay, and this is just a modern example. If you go to a glacier in Iceland, a lot of my photos are from Iceland because I was there. I went there, this is probably 10 years ago now. But there's just this huge volume of meltwater coming towards you. It's looking sort of up back towards the glacier. The glacier is off to the right here. You can see how muddy the water is. So and it's moving very fast. There's a lot of water moving through this. This is another example of an ice margin and an outwash system that's mostly sand and gravel. This is an air photo of another glacier from Alaska. I don't know which one this is either, but the glacier is off to the right here, and you can see there's a stream coming off, melting, transporting sediment. So we would call that material outwash, and we would call the material that's being deposited by the glacier till. Okay, and so the idea here being that till is sort of associated directly with the ice, and outwash is associated with material outside of the ice. And as I mentioned, if we sort of zoom into Indiana here, this is a map showing you these major meltwater pathways that would have occupied the Wabash Valley, the Eel River, the West Fork White River, East Fork White River, the Ohio River. Most of the major river corridors in the Midwest actually were former pathways for this meltwater. And they may have looked something like this. Again, another modern example from, I think this is New Zealand. But these very distinctive, this is what they call a braided river system, a lot of sediment and a lot of water moving through these systems. So, and one final material that I want to talk about besides till and outwash is loess. Also, that's the deposit of silt and clay that was picked up by the wind from, for example, outwash plains and deposited somewhere downwind. We also call that dust. So wind-blown silt and clay. And this image here is a satellite image from Greenland, and this big plume of the white stuff that you see, that's actually wind-blown material. That's material picked up by the wind up into the atmosphere and is being transported, in this case, to the south and east. And I have some other photos that are sort of like, this is what you would see on the ground. So you can sort of see across this valley here is the Ouabache Valley, and then you can see sort of this hazy look. That's actually silt and clay being blown up out of the valley. You know, I mean, you've all seen sort of videos of dust storms, things like that. It's sort of like that, a little bit different in that this is sourced from glacial material as opposed to being sort of desert type dust storms, but it's the same sort of concept. It's large volumes of silt and clay that are being transported by the wind. Another example from the Delta River in Alaska, you can see an outwash surface here, and then this sort of hazy stuff. That's all stuff that's being blown up into the air. So if you go far enough downwind, the material falls out of suspension through the air, and you get a deposit that we call loess. And so this is from Tennessee, actually. Not OSHA approved ladder, by the way. I'm glad there's nobody on the ladder currently. The photo was taken. But this material is very homogeneous. And actually, most of the surface around Terre Haute is composed of loess. Because again, the Wabash Valley would have been a big source. And you have probably between 10 and 15 feet of, I don't know if anybody has more personal experience than that, but you probably, if you've dug a foundation or something like that, you probably have at least, the closer you are to the valley, the thicker it's going to be, because you're closer to the source. But it's about 10 or 15 feet thick here, all the way down from Terre Haute all the way to Vincennes, Mount Vernon, Evansville area. So the closer you are, and I'll show a map of that in a second, the closer you are to the source, the thicker it is. Here's just another example of, this is along the Missouri River in North Dakota, showing you this very distinct material that's sitting on top where that gentleman is standing with the red shirt. He's standing right at the base of other glacial sediments, and then that material above it is wind-blown silt and clay. Okay, so we saw that image, we saw that one. The distribution of this wind-blown material is very widespread throughout the Midwest. You can see that on the map on the left. The map on the right shows sort of the same thing. The thickest loess is adjacent to the Missouri and the Mississippi rivers, like we're talking 50-ish more feet thick. Along the Wabash, it's not quite as thick, or the Ohio or the White Rivers, they're not quite as thick. But that is the pattern of loess. One other thing, I sort of mentioned this already, this is just another map showing or trying to tell you that the loess is thickest adjacent to these major meltwater pathways. So all this is relevant because we're gonna, at Atherton Island, there is loess there, okay? And maybe one reason why it's important, just as a sidebar slightly, is that loess soils cover about a third of the state of Indiana. And so they're very productive from an agricultural point of view. They have, they're finer grained, they can hold moisture, they can hang on to the organic matter. So they're really productive soils in Indiana. So that's why I showed this. This is a basic soils map of Indiana. And the yellows, for example, this excuse me, this yellow, this green, and these two, number 9 and 10, those are loess-derived soils, so they have loess in the soil description. Okay, so hopefully that wasn't too long of an introduction, but that's sort of an introduction to sort of some glacial sediments, a little bit of history of, not a history of the science, but a little bit of history of how we got here, how do we know what we know. And then the last 10 or so slides are just going to be about Atherton Island. So with all that background, some of you, or you've seen this map before. So Atherton Island is a very, very interesting place because, for one thing, it's right at the edge of two different lobes of the ice sheet. And lobes are just sort of different divisions of the ice sheet, basically based on where the ice was flowing. So these big arrows with Lake Michigan and Huron-Erie and Green Bay and Superior and Des Moines, those are all, we call those lobes of the ice sheet, basically just signifying, the arrows signifying the direction that the ice was flowing. So ice would have been coming basically down the long axis of Lake Michigan, north-south, and sort of spreading out into central and sort of south-central Illinois. And so this area sort of here is what we call the Lake Michigan lobe. And then you had ice also, it's the same glacier, but it's a different part of the glacier. It's coming more down the axis of Lake Erie and Lake Huron. So we call that the Huron or the Huron-Erie lobe. And so most of the deposits in Indiana, if you go east of here, they're mostly the Huron-Erie lobe deposits. But Atherton Island is unique because there's this little piece of Lake Michigan lobe deposits that sort of butt right up against the Huron-Erie lobe. And I'll show us more images of that. The other thing that's unique about Atherton Island is that it has two different tills. So it has the most recent till, the Wisconsin till of the Lake Michigan lobe, and it has an older till, an Illinoisan till. And it has loess, so which we just talked about, Wisconsin aged loess. And it has a paleosol, has an old soil that developed in the time period between the most recent glaciation and the penultimate glaciation, the Illinois. Okay, very, very unique. You don't find many places where you can see this, especially in an exposure. You know, a lot of times we have to take sediment cores, and that's great, but it's nice to be able to see things in sort of quasi 3 dimensions, or at least in a big exposure, which we have in Atherton Island. Okay, so we're going to zoom in to where the box is there. I know it's hard to see, but this is the whole state, the image that I showed before, Ohio, Indiana, Illinois. The green is basically the limit of the Wisconsin glaciation. So again, we're right at the edge of the Wisconsin glaciation. The yellow is big meltwater pathways, the Wabash. Okay, and there's been a few publications and ideas on how, most of you probably know that, of course, the island it's not really an island. It's just surrounded by river valleys on 3 sides, or on all sides really, which is really unique. You don't usually see that. And so this has been of interest for a long time. I mean, this publication is from the 50s or the 60s. I want to say it's from the 60s. But they had a lot of similar ideas that I'm going to try to share here. So let's see what I want to show about this. This is just an old map showing the distribution of different types of sediments. I think the next one is actually going to be a little bit more colorful, so I'm just going to skip to that one. But it's showing the same thing. Okay, lots of colors here and lots of sort of explanation to do here. So the colors are just different materials. The tan is till of the Wisconsin age, and the maximum limit is this red dashed line. So you can see Rockville there, all this stuff here in the upper right, that's the Huron-Erie lobe. And then you can see where Clinton is along the valley, along the Wabash Valley. And then you can see everything to the west of that, that's Lake Michigan lobe. So, and then, I don't have a pointer, but Atherton Island is this sort of oblong shaped thing right here, right? So Raccoon Creek is on its sort of eastern end, and then the Wabash Valley is on its west end, and then it's sort of this green thing, which is actually outwash, sand and gravel from the last glaciation. So it's sort of surrounded on all sides by river valleys. That's unique. Let's see, what else do I want to tell you here? I guess one thing is that the terminal moraine, so the end point for the Lake Michigan lobe, you can see that dashed red line just to the east of where Clinton is labeled. The west end of Atherton Island is the terminal moraine for the Lake Michigan lobe. So when I show you the next few slides of this large outcrop, the very top of the outcrop has till deposited by ice flowing from the west. Okay. And of course, the Wabash Valley comes north-south directly through Clinton. The green colors, again, are these sands and gravels, these outwash meltwater deposits, which would have been a source for the windblown material to come up out of. So we'll see evidence of that.
What's purple?
Purple is Illinoisan till. Yeah, purple is Illinoisan till. So, sorry, thank you for that. And actually, in yellow are sand dunes. So Aeolian sand. So these are, again, 15 to 20,000 year old dunes. You know, you might think of dunes as being like, well, Indiana dunes and along the modern Great Lakes, which are good places, but there's actually a lot of old sand dunes away from any modern lakes, right? This is just, you know, if you go to Rosedale, north side of Terre Haute, there's sand dunes all over the place. So, okay, let's see.
Any question?
Yep, sorry.
Okay, so,
I'll go back.
just did a little bit of studying I've done about Atherton Island according to what John Whitaker said. So the Lake Michigan lobe, or the water from Lake Michigan got here first, and then the Huron-Erie, and because what he had said was that the Wabash used to flow on both sides.
Mm-hmm.
And then looks like to me that the Huron-Erie lobe then came in and pushed Raccoon Creek up, so that instead of having the water flowing down, it's flowing down on one side and then it.
Yes, I mean, that's a good hypothesis, I would say.
Okay.
So, if you remember T.C. Chamberlain, one of my favorite things about T.C. Chamberlain is he was he's a big thinker, but one of his things is the theory of multiple working hypotheses, which I really love, because it's like, and even preparing for this, I was like, well, you know, all these different ideas for why Raccoon Creek does this, you know, it goes to the southwest and then it takes a dog leg. Why does it do that? And there's, again, people have been interested in this for a long time. And even when you read all the stuff, it's sort of like, well, I don't know how to test all of them. Then this is geology too. So as you probably know, I mean, geology is deductive mainly. So it's already happened. So we have to try to figure it out from geologic evidence. We can't experiment on it's hard to experiment on the landscape, try to recreate this experiment. But the other reason that it's tough is because most of this fill here, this outwash fill, it's all sand and gravel. So there's a lot of part of which is generally easy to erode. Okay, so, and to your point about like what was the exact timing, when exactly did the Lake Michigan lobe get there, we have decent control from a geologic perspective, but not like you know, daily or weekly. This is like in the hundreds or thousands of year scale that we know when the ice sheet came, when the ice sheet left generally. But we don't know the details of, well, okay, so the Lake Michigan lobe presumably basically you could argue that actually the Wabash wasn't quite there. It formed after the Lake Michigan lobe retreated. So at the maximum Lake Michigan lobe, water was probably flowing, as you said, it was probably flowing, it was flowing down here and down this way to the south. Did this ice retreat before that ice? And it's, again, it's like, we can go through all the hypotheses, but I don't know which one's right. I just know it's very strange. And most places, and I didn't really mention this and I didn't put a slide in it, but when you look at the way that drainage networks work, and maybe this is overkill here, but this is the reason that this is unique is because most things, you almost never see that change in direction of flow unless there's some blockage or something. So it's like I don't have a great answer for which one is like a preferred hypothesis. I mean, obviously it happened. I mean, there's one idea that, well, there was just meltwater coming down the Wabash, and there's another thing that I didn't mention, but a lot of times when there's a tributary to these big meltwater streams, because the meltwater stream is actually depositing a lot of sediment, that these tributary streams, they don't get cut off, but they essentially get back flooded because they can't, they don't have very much water flowing through them. And so essentially a lot of these tributary valleys to big meltwater streams get back flooded. And so you can basically get lakes. They call these slack water lakes. So you've all probably been to Goose Pond, right? Most of you have been to Goose Pond. Goose Pond is a great example of a slack water lake, meaning that there was a river system that was graded down to the West Fork White River. But when that river started to build up, essentially through sedimentation, that tributary valley couldn't basically keep up, and so it back flooded. Okay, so the reason that it's really low lying there and wet is because it was an old slack water system. And you can find these little things up and all up and down the Wabash, the White River, Ohio River, Mississippi. They're very, very common things. So one idea is that, well, maybe this sort of back flooding of like an old version of Raccoon Creek, and then there was sediment that was deposited in that lake, and then when the lake drained, there was a little bit of a high spot, and then there are sand dunes like near Rosedale that maybe blew up, and that caused enough relief. Again, most of you probably know it's not like it's 500 feet between, Rosedale and the bottom of the creek valley there. It might be 20 or 30 feet. It's not very much. So these are pretty subtle things. So, and I can entertain more questions on that specific thing, but I just want to get to two more things, or really just to show you what we found at Atherton Island, which is hope you'll find interesting. So we're going to zoom in one more time and go to the very west end at the preserve where the star is. And this is one example. This is the biggest. So what you're seeing here is standing in the creek bed, basically looking up. There's a large exposure of glacial sediment. I know it's hard to see, but the next image will show you what is actually there. So in this image, there are actually two different tills of different ages, and there's a loess layer in between. So what we have found here is on the left. So what we call this a stratigraphic diagram, a stratigraphic column. And the gray with the little triangles, that's till. And so there's till at the very top, and there's a bunch of numbers there. It's like, what are those numbers? Those numbers are radiocarbon ages from the dating of snails. So it's kind of a cool thing. And when we were first there, Jim mentioned that he had noted snails or gastropods for a long time there. And so when you spend enough time looking at that outcrop, you see things like this, various genera of gastropods. So you can date. You only need a couple, 2 or 3, to get a radiocarbon age. And so these numbers here, this 24,640, those are radiocarbon ages, again, on gastropods. And so we did that many different levels, as you can see. And so 24,000 all the way to about 37, 38,000. And most of you are familiar with this. That's great, because the stuff on the bottom should be older than the stuff on the top. That's a good test. If it was flipped, I wouldn't be showing you if it was flipped, because I'd be confused. And this is really cool because we can date gastropods. And another thing that's cool is that some of these don't live in Indiana anymore. Some of them do. Some of them are pretty general, so they live in Indiana today. But some of them, especially this guy, the genus Vertigo, some of those only are found like at the latitude of like Lake Superior in north in Canada today. So that makes you think, well, it was much colder, which is not a super surprise. This is like the peak of the last ice age, but the gastropods are telling us that not how cold it was exactly, but we can constrain it by knowing, hey, we find these same gastropods in the modern setting much further north. So this is and this has taken a couple years to get all this together. We have a lot more data that I'm not going to show because it's sort of boring, sort of super into the details of the particle size of the silt, the magnetic properties of the silt. We can do things like the mineralogy of the clays and the silts and geochemistry. All this stuff doesn't really matter for you guys. Just to know that there actually is loess. So this is windblown silt and clay that's sandwiched between two tills, which is we don't see that a lot. And actually most of the outcrop, if you go back to the photo, and if you just stood there for a while, this lower part is actually mostly that Illinoisan till. And actually for the first couple times we were there, we were like, we didn't, it's a good example of sort of scientific progress and thought just in the small scale, even with me, because it's like we first went to this outcrop and we thought, well, we're right at the terminal moraine of the Wisconsin glaciation. I'm like, this is all Wisconsin. It's all young stuff. And like, I guess take a look and get a few samples. But then we realized at the very top, there was this really cool record at the top with snails that we could do radiocarbon dating on. Okay, so with that, I'm sort of going to conclude and just say Atherton Island's a really, really unique place. I don't have all the answers for exactly why Raccoon Creek is the way that it is, but it definitely was probably an island at some point in time, meaning that it was probably surrounded by glacial meltwater coming the reverse direction, modern Raccoon Creek during the last glaciation. There's a Wisconsin till at the very west end, terminal moraine of the Lake Michigan lobe. There's also the Illinoisan till. And with that, I will take any questions and thank you for your time.
Global warming
Yes.
began when?
Which one?
Began when?
Yes.
What type?
Exactly.
Exactly. Well, there's been periods of Earth history, as you saw here, there's periods of Earth history that have undergone natural big fluctuations between having very little ice on the planet versus having like 20% of the northern hemisphere covered by ice.
All right. What caused it?
Scale.
There's a lot of reasons why. It's complicated, but it's the carbon cycle.
The carbon cycle? What caused the carbon cycle about 25 million years ago, or 25,000 years ago?
Sorry, what caused the?
Carbon cycle to cause global warming to begin.
Very good question. This is super complex. I mean, it has to do with the ocean, the atmosphere interacting with one another. If I could step back for just a second, I would say a lot of the ideas for this are based on the Earth and Sun for the last 2 million years or so, the Earth and Sun geometry. So basically, how much solar energy are we getting changes over time. The total amount actually doesn't change. It does change a little bit, but it's the distribution of that solar radiation because of changes in the Earth's tilt, changes in the we call it the eccentricity, basically how circular the orbit is of the Earth around the sun, and also there's precession, which is sort of the wobbling of the tilt in a way. So those three, the leading idea is that those three things help drive you to help grow an ice sheet, a glacier in the northern hemisphere.
So,
And,
mankind
yes,
didn't create a glacier from melting.
correct.
All right. So, that means something else did, correct?
In the past, yes,
All right.
yeah.
What I think, or what I surmise, it seems to me that our Earth automatically goes from hot to cold. During the dinosaur periods, it was extremely hot, and dinosaurs lived clear to Alaska.
Mhm.
Now it became extremely cold, and only Neanderthals and other small, short, stoop
Yep.
things
Yep.
could move on the ice. But now we're back to heating up.
Mhm.
And once we begin to heat, we don't stop until the earth sets. In
Yeah.
other words, the tilting sets.
I see.
Human
Mhm.
can cause some of it,
Mhm.
but most of it is not caused by humans.
That's true in the geologic past, yes.
Yes.
In the geologic
And so
past, yeah.
this is where I'm coming from.
I have
I
a
get you.
question.
Sure.
You showed us that the going up and down there.
Yeah.
And it seems like as you got more toward modern time, that
Yep.
the variations were larger. Is
Yes.
that, do people make, is there, what do they, what?
That's a very good observation because that's one of the bigger conundrums. There's actually a name for it to tell you that how scientific. They call it the mid-Pleistocene transition. So it's a very astute observation that the and we could go back here just to show you. But the cyclicity, so the wavelength and the amplitude of the glacial cycles is about 40,000 years back before about 800,000 years ago. You can sort of see the, and then after that they become more extreme and spread further out. I don't have a great answer for you because there's a lot of ideas. I mean, a lot of these things are related to how the ocean and the atmosphere are connected, how ocean currents redistribute heat. You have to, in this geologic, if you go back far enough, you'll get into things like tectonics, so like mountain building. We're not quite at that scale yet, but here in this short time view, but there's a lot of different processes going on in the earth, in the atmosphere, in the ocean, on land, that are all coming together to make this record. And you know, it's not a perfect. You see, it's not like it's just I don't know, a smooth on and smooth off. It's very chaotic, right? And like a good example would be, you know, in general, like we just went through an El Nino year, right? And it's like, well, okay, we have this expectation for the Midwest. And well, sometimes most times it's that, but sometimes it's not. It's not always going to be, it's not always going to be a hot summer. There's variation. So it's a long way of saying I don't know, and it's still sort of somewhat of an open question why that change occurred. But yeah, that's a good observation.
When did Lake Michigan form? When did it get kind of, stuff get taken? That was a glacier too, that did that.
Yep, so probably before any glaciation, before any of these glaciations, if they ever reached the latitude of Lake Michigan, it was probably a river system. All the Great Lakes were probably river valleys that probably either went to northward to Hudson Bay, or maybe they went sort of in their current configuration to out to St. Lawrence. And so once the ice came though, those valleys were sort of scooped out essentially. I mean, that's sort of the broad view of it. So the sort of scooping out process, if you will, that's probably been multiple glaciations to actually scoop it out. Now the modern version of Lake Michigan depends on how detailed you want to get. So the Lake Michigan lobe started to retreat. You can go to this slide here. Like the very southern end of Lake Michigan, Gary or Chicago, ice was there about 16,000 years ago. As we were coming out of the last glacial maximum, ice is retreating north about 16,000 years ago. As ice continued to retreat, there was a much higher level of Lake Michigan. We call that Glacial Lake Chicago. So that existed 40 or 50 feet higher than the modern lake. Up until, let's say, about 12,000 years ago. Basically until ice retreated more or less north of the Straits of Mackinac in Michigan, into the UP, basically. And then actually the lake dropped a lot. And maybe some of you know, but there are actually stumps in the bottom of Lake Michigan from that period about 7,000 or 8,000, between about 8 and 10,000 years ago, when the lake level was much, much lower than it is today. And then since then, it's risen up to more or less its modern level. That's sort of the simple story. So it was high, it was low, and then it's sort of back. It's not as high as the glacial lakes, but it's in between. So, yep.
I know when ice sheets retreat, there's some level of research of the whole continental plate. On what time scale does that happen, and could it contribute to any of the differences in flow at the level of Raccoon Creek?
And you're talking about what I would call isostatic rebound?
Yeah, the rebound.
Okay. So the idea there is that, just think of it like, I don't know, you have a mattress and you have a bowling ball, you put a bowling ball on the mattress and it depresses the area around the bowling ball, and you take the bowling ball off and it comes back up, right? It's just sort of not the exact analogy, but similar. If you put an ice sheet on a continent, it's going to do the same thing. And so, and to your point, we're talking if you were to measure this in absolute terms, we're talking hundreds of meters that the land surface has adjusted, but it's all relative to everywhere else, so we don't feel it. Just we're spinning on the planet Earth really fast right now, but we don't know because everything else is spinning fast. So everything is rebounding. And just a side note, one of the cool things today with modern technology and GPS, super high precision GPS units, they put these out all across the country and the continent. You can see that there are places on the north shore of Lake Superior that are millimeters per year that are uplifting. The ground is actually moving up.
Well, right. So I'm wondering, is that happening? You said per year. So could that happen at the level of, it's retreated in a mile or two?
And
right?
that's
Is now able to flow north a bit because it's
yes.
rebounded south.
I think that's a reasonable hypothesis. Again, one of the reasonable hypotheses for the reversal. But just to point out, as you say, sort of in your question, it's a relatively short distance, so the relative difference is not going to be very big. The relative difference between here and Hudson Bay, that's a lot. But the relative difference just within Raccoon Creek, that little area there by Rosedale, like it could be. The other thing too is that the rebound is most rapid right when you remove it. Right when you remove the mass, the greatest amount of rebound effect is in the beginning, and then it slows over time. So.
What about, how thick was the ice on Atherton Island?
So on the west side, probably where the preserve is, it might have only been 100 feet, couple hundred feet thick. I mean, I know you hear about, well, it was a mile thick in Indy. Well, I don't think it was that thick. There is a physical limit, or not a physical, a physics-based limit to how thick you can get an ice sheet. And that's in the order of like 3,000 or 4,000 meters, so that's like 12,000 feet. So yeah, at this, but I'm talking at the center, like way up in Hudson Bay. So it might have been 1.5 miles, 2 miles maybe, thick at the maximum. And then again, obviously it thins towards the edges. So, but here I would say a couple hundred feet probably. So.
Do you know where there's that rounded area sort of building in?
Like this right here?
That thing,
Yeah. That's a good question. That's a bedrock story. So, I mean, most of you have been through probably part of that. You know, basically from Bloomington south, more or less. I mean, you don't have to go very far east of here to get into that. And my hypothesis would be that basically you're right near the limit of the Illinois glaciation, and the ice is thin, and it can be influenced by small changes in topography more easily when the ice is really thin. So if you have these big bedrock hills, ice just isn't, it's, you know, path of least resistance. It's not going to want to go up over these big bedrock hills. It's just going to sort of go in the valleys or just die out in a way, stop. And so that's why it's a bedrock related to where the bedrock outcrops. On the east side, on the very east side of that, so if you go from Louisville basically up towards like Columbus, if you're familiar with the Knobstone Escarpment, which probably most of you are, that would have been a pretty severe, you know, block of ice. I mean, it's a couple hundred feet, right? So ice would have probably advanced up to that and had a hard time getting up over that. So that would be my answer for its bedrock thing. So yeah, I'll get to you.
How do you explain the black soil? If you go over across the state line up in Paris, Illinois,
Yeah.
how do you explain from there clear way over
Yeah.
that it's so black?
Yeah. So it's a little hard to believe what the landscape would have looked like pre-settlement, right? But that very likely would have been prairie. And that's why it's black. So grasses, a lot of their biomass is under the ground, right? So, and maybe Jim can speak to this a little more even. But yeah, I mean, most of soils in Illinois and some soils in Indiana, mostly in basically west central Indiana, that was the former sort of essentially natural eastern edge of the prairie, tallgrass prairie.
So in 18,000 years of growing and
Yes.
decomposition,
Yep.
formed black organic matter.
Versus a eastern hardwoods forest soil, more acidic, right? More acidic. You got trees. So the soils they're not bad. They're just not as dark because trees, they're above ground biomass, right? Grasses are below ground. So you have, as Phil said, you have 18,000, you have 20-ish thousand years to accumulate, you know, grasses, you know, essentially grass roots in the soil. And then over here, as you go east, of course, we're in Indiana, we're sort of on the western edge of the forest front, basically. We're at that zone between the forest and the prairie. So in the west is going to be more prairie, east is going to be forest. And if someone has more than that, they can add to that. I'm a geologist, so. Yeah.
Two questions. How deep below the ice did the aquifer freeze?
Ooh. Did
And
the aqu-
when the ice sheet retreated, was some of the rise due to absorption by the aquifer of the remaining waters?
Very interesting question. Boy, that's a good one.
Because some of that ice, actually the water is still here.
Oh yeah, yeah, yep, it is. Yeah, I mean that's a hard one because you can go to places today, and I'm not a permafrost expert by any stretch, but I think sort of what you're talking about might be sort of like permafrost. I mean, it's frozen ground, right?
Well, it's
Or you
frozen
just like-
ground deep
Deep.
into, like, Terre Haute sits above an underground lake, which is part of our aquifer, which was.
Right.
It's
I see what
very
you mean.
good size. But it would have had to be, I would have thought, either been flowing underneath the ice sheet.
Right.
Because you get a layer between the bottom of the ice sheet and the soil itself, but then you go a little bit deeper and you get into the aquifer, and it's
Right.
still water.
Yeah.
It's still.
From
it's
that.
Not, it's not frozen.
Yeah. Yeah, no, it's a good point. I think one thing I would just say, well, it's a little more subtle than a river, right? I mean,
Yeah.
this is space between grains, right?
Yes.
And so when we say underground river, I know what you mean. It's not actually a flowing river. It's water moving very slowly.
And it's being absorbed.
Yes. So yeah, I'm trying to think how to answer that. I mean, it's a tough one to answer because it's like, sure, underneath the glacier you would have had sediment that would have had water in it, in between the pores, in between the grains, and as you said, basically a lot of that meltwater infiltrated deep into the like deep.
It wouldn't have been frozen.
And it would not have been frozen. And like you said, it's mostly still there unless we pump it. So yeah, I don't know. Sorry, I don't know if I can answer your question specifically, but I think you have the right thought process. Like, yeah, there is aquifer, there is groundwater that is very old, that is glacial aged, that's 20,000 years old.
So what would be the depth of freeze if the ice sheet was there? 50, 60, 100
The ice
feet?
insulated. The ice is
Yeah, I mean, it's
It's not gonna freeze very deep.
yeah.
It's
I
not
mean,
gonna
there's
freeze.
a geothermal gradient, which is pretty small, but as I said, like there is an insulating, like you'd have to get it. The reason that you get like permafrost in Alaska is that the air temperature gets really cold, but underneath the glacier you're insulated to a certain level, right? You're actually not going to get below zero probably, so you're probably not going to freeze anything. It's going to be cold water, but yeah. So, yes.
Changing the subject,
Sure.
but if we want to go and hike Atherton Island,
Yes.
when it opens in June, what do we expect? What does it look like?
Jim, Jim Nardi could answer that question.
You can answer that.
It's a diverse.
The only thing is there are these deep, I don't know, Jim, if you call them gullies or stream valleys that are cut. Some of them don't have flowing water. Like, for example, there's this little creek here that's, I mean, you can walk across it. It's probably this wide, right? In low flow. I don't know what it's doing now. I'd be curious to know. It's pretty good flow probably. But like a lot of these little gullies here, this goes back up. There's no water, there's no permanent water going through those. So point is that it's a pretty, when you're up high, okay, you're up high and you can, some rolling hills, but then when you go down into these valleys, it's pretty rugged. You're right at the edge of the Wabash river valley and coming up basically onto what was the terminal moraine. So, yeah, rolling hills. I mean, definitely, I don't know, rolling hills, but
Area is it?
how large?
250 acres.
And where's
The
the,
entire island?
No,
No,
Just
just the
the
west
preserve.
Yeah.
west side.
Atherton Island was all the way
Yeah.
to Loope.
Yes.
and where's the access point?
It's
Is it-
on 800 South Road, it's a county road. The access is about 1 mile east of Lyford.
Yeah, 6540 West 800 South, Rosedale, Indiana.
This is what you would be seeing most often.
Yeah, I don't have on that.
It's a combination of undisturbed areas such as this and areas that we're trying to restore that were formerly agricultural. So we've done a lot of tree planting. We've planted prairie flowers and prairie grasses. So we have a few acres of pollinator habitat, but most of it is forested.
Yeah.
Beautiful place.
The Longhorn.
Oh,
Yeah, it's, Coxville is on the east side of Atherton Island, and the nature preserve is on the west side. So, and the island itself is about 4 miles wide at its widest.
So the till that was once over top of Terre Haute is dispersed everywhere south Mississippi. Do you guys track that too?
You mean sort of what happens to that when it gets eroded?
Right. What
Well-
river, Wabash River took away from us and
Right, yeah, I wouldn't say I necessarily track it. But yes, I mean, there is, I mean, it goes, as you know, it goes on now. Every time
Terre Haute soil till could be in Gulf of Mexico about 50 years.
Oh, yes.
it could be, yep, yep. Well,
That
and
wouldn't have started until
It-
the 1800s. Before that, it was
Yeah.
all being captured by the forest and the
Yep.
Prairies.
Yep.
That's why Wabash is the White River. It was so clean, no sediment.
And you probably, if you spend enough time, especially in hilly landscapes near old fence rows, you'll see exactly that. In that, sometimes those fence rows would have captured that soil runoff from the field before it got to the stream, and so you can see on one side of the fence you see a buildup of soil that is from the field, adjacent field, and then on the other side of the fence, it's been removed away because the fence was there preventing it from moving. So if that makes sense.
Thinking back at the glacier recedes some of those guys.
Oh yeah.
Because the land,
I see,
land
yeah.
we're on top of here now would have been level all the way over to Illinois.
Yes.
And then when the melt comes, all that disappeared.
Yep.
Over tens of thousands of years, and it's, and all the southern states got all of that good soil.
Yep. And so yeah, you could take a sediment core in the Gulf of Mexico, and you could find, yep, along with Missouri River, Mississippi River, Illinois River, all the other tributaries that would have contributed. So, yes.
So I moved from Terre Haute, right downtown,
Mm-hmm.
to West Terre Haute. The soil was completely different.
Mm-hmm.
It's like fine, dark soil in Terre Haute, it was, when
Okay.
I was gardening and stuff. And then moved over and it's clay. Which of these things explains mine?
I mean,
Totally different from Pennsylvania where I came from, where you
Yes.
couldn't dig anything.
Yes, and if anybody has any better answer, please raise your hand. My thought would be that Terre Haute sits on an outwash terrace, right? And it probably was prairie, pre-settlement. I don't know if that's entirely accurate, but it's probably true. So that's probably why it was dark. It's probably sandy, generally sandier. And then on the west, and even here, if you dug a hole here, it would be mostly loess. You would go from loess into Illinois till here, like right here. So that would be the difference. So it's very sandy and probably prairie soils in most of the city of Terre Haute, and then you go east. Once you go up the bluff and to the east, it's all going to be loess and till.
Looks like Devon Park, that hill is sandy, at least the top of it.
Yes, and those are sand dunes. Those would be sand dunes coming off of the. Yep.
Yeah, I know it runs all the way down. I mean, is that the same sand that ends up in Oaktown and where they go to the mountains and stuff like Merrill?
Yes. Yep. Same exact. Obviously, it's way further south, but
Is it like a high bank of the Wabash at one point of the glaciation or the drainage?
Do you mean the dunes, or you're saying that's the high?
There's a ridge all the way along there, I would say.
Mhm.
And some of it, there's some, you don't see any bedrock, but I suspect there's something.
There's some close, yeah. But yeah, no, you're right. Those they stretch all the way to. All the way to not even past Vincennes too. New Harmony.
Right,
Keep going all the way down. There's dunes all over. So yeah, melons are good for that. So. Any other questions? Oh, yep.
So would the cliffs at Merrim be
Yep.
formed by glacial movement?
Probably partly. When you have these big volumes of water, you can erode rock. So there's sandstone at Merrim, right? The bluffs there. So yeah, the modern river doesn't have much of a chance to erode into it because it's in a single channel, and when it floods, it fills the floodplain, but with relatively low flow. So there's mostly deposition. Whereas during the glacial time, there would have been more water and more sediment to be able to actually erode into the sides of the valleys. And the river would have been not just in one small, Wabash isn't small, one single channel. It would have been, I think I showed a photo of there might have been 15 channels interspersing one another, and that's what it would have been like. So there would have been chances for that river to widen the valley basically and erode into whatever was there. So in that case, it was sandstone rock. So it's a good question.
Back to lives. It was nice and warm during the dinosaurs.
Mm-hmm.
Then a meteorite hit the earth, creating an ice type situation throughout the earth.
Sure.
And then the dust and such cleared the air and melted the glaciers, right? Is that what you're saying?
Not directly if you're talking about, there wouldn't have been many glaciers at that time, at the end of the Cretaceous. It was really warm, really warm, as you pointed out. It was tropical almost from the equator to the poles. So, but yeah, there would have been a very severe change in climate because of the dust, because of the fires, and it probably cooled down significantly. I don't know of evidence that it either lasted long enough, or you have to think too that you need land for glaciers, right? So it can be as cold as you want, but if it's the ocean, you're just going to form sea ice is what you do. So to form a glacier, you need to have land for the snow to accumulate, right? Then snow turns to firn, and then firn turns to ice. So yeah, and that's why the Northern Hemisphere, we don't talk a lot about glaciers in the Southern Hemisphere because there's less land there. That's part of the reason, right? And it's maybe not distributed completely, except Antarctica, which is, they're actually isolated. It's isolated by a ocean current. Okay, but your point is that, I mean, I would say there probably weren't, the end of the Cretaceous, the end of the dinosaurs, that was a really, really warm period in Earth history. There probably weren't many glaciers there to begin with.
Oh, no.
But
I mean,
you're saying after that. It's possible. I don't.
It takes a while for our climate to rinse out the dirt. that
Sure.
we put
Yeah.
in.
Yep. Yep.
Our clouds and our rain.
Mhm. Yeah.
Do you have an explanation for, why they found like woolly mammoths and other animals with food still in their mouth and they're done?
That correct.
Yeah, I think that would be a. Depends on the. I mean, it's all about preservation, right? So, I mean, yeah, you can imagine a woolly mammoth that's. I mean, it would take a unique situation. You may have heard of like the La Brea tar pits. Have you heard of the La Brea tar pits? Southern California. It's a natural oil seep, and these megafauna would go there. This is, again, during the same time period we had glaciers here in Indiana. It was a much different climate in California. They didn't have glaciers. They did in the mountains, but not in like the LA basin, for example. But these megafauna would get stuck in this oil seep, basically. And it's like, boom, they're preserved because they probably just sink down in, and it's like, so that's one way. Another way, well, they're big, and sure they can sink into the mud, but then you still have to be buried quickly,
Well,
right?
Because
Now-
they supposedly like flash froze or something.
Yeah.
Well, and I think maybe like this I don't know if you're referring to some of them in Siberia, for example.
Right.
And that's a little different because there's permafrost and it gets really, really cold. So like it could die and, like you said, sort of be flash frozen. Whereas here it was cold, but it probably wasn't that cold, just because we're at like 40 degrees north latitude. We're closer to the equator than we are to the pole. Whereas Siberia, yeah, it's isolated. It's 60, 70 degrees north latitude. Continental setting where you don't have any warm air from the oceans impacting, so it's really, really cold, really dry. That might be a better explanation than, sure, like a mammoth here could, sink into the mud or something, and get buried, but it's still pretty warm. You'd probably still have scavengers coming and taking it. So maybe, I don't know.
I think they were frozen in the ice, and they actually had to wait until the glacier
Melted, yeah. So they've been frozen for tens of thousands of years. That's maybe the other key too. Like the ones here wouldn't have been frozen for that long, if there were such a thing here. So. Anything else? My email is hloop@indiana.edu in case you have more questions.
I live on the east side.
Yeah, I talked
Okay.
about farming.
South of Knoxville.